I will try to start more or less on time. So welcome to everyone to this second meeting of the SICC Talks on Complexity. Today we have two speakers, again, as the usual format. The first one is Eckehard Schöll, and the second one is Florian Dörfler. They agreed to do two presentations on a common topic, which is synchronization in power grids. And I think it will be very nice to see the different perspective and the different ways in which they approach this topic. So let me shortly introduce Eckehard Schöll. He is a professor of theoretical physics at the Technical University of Berlin. And I mean, it's very difficult to introduce him, because if you want to mention a few results, it's very difficult to select among a rich repertoire of different very good works that were initiated by him and his group. I'm thinking about chaos control, Chimera states, now neural networks, neurodynamics. So he's really a big name of nonlinear dynamics and its implication. So it's really a pleasure, I think, for me and for all the audience to have this opportunity. And without other words, I will leave the floor to Eckehard and thank him for accepting this invitation.
Well, good afternoon. Thank you very much, Mattia, for your kind introduction and for the invitation. It's a great pleasure and an honor to be here and present my results in your workshop. Results which bridge between neuroscience and between the modeling of power grids. So the title is What Adaptive Neuronal Networks Teach Us About Power Grids. This is work done at TU Berlin and also at the Bernstein Center of Computation for Computational Neuroscience in Berlin and at the Potsdam Institute of Climate Impact Research. So let me give you some outline after. Well, the whole talk is centered around controlling nonlinear dynamics in complex networks. And after some motivation and introduction to synchronization patterns, I will first give a brief review of adaptive neuronal networks, in particular multi-frequency clusters, and then come to synchronization of power grids. I will present methods of feedback control and deal with solitary states. And finally, I will show that power grids can be conceived as pseudo-adaptive networks, and we can learn something from adaptive neuronal networks. In particular, we will identify the power flow along the lines as pseudo-coupling weights. So networks, complex networks, are abundant in our world, and it's only 1 week since the Nobel Prize in Physics was announced for the field of complex systems, 1/2 to Syokuro Manabe and Klaus Hasselmann for their physical modeling of climate and global warming. So this is a network, a complex network, the system Earth, the atmosphere, and the ocean. And the other half was announced to Giorgio Parisi for his fundamental groundbreaking work on the interplay of disorder and fluctuations from atomic to planetary scales, spin glasses, surface growth, roughness, phase transition. So this gives particular prominence to the field of complex systems and complex networks. And I will give you some more examples. The brain is a complex network. The internet, power grids are complex networks. And in particular, here you see the power grid of Germany with loads marked red as red dots and generators marked as green squares. And you see it's really complex, and we want to maintain a stable state of synchronization. If that fails, this is what you get. This is a real blackdown which happened 18 years ago in the northeastern United States. But further on, social networks, socioeconomic networks all sorts of supply networks are examples. And I will give you a few, I will make a few words about synchronization and desynchronization, because sometimes synchronization is desirable, like in communication or in power grids or in the brain when you deal with learning and memory, but sometimes it's also undesirable. For example, this is the London Millennium Bridge, which was closed down 2 days after its opening in the year 2000 because of unwanted and dangerous lateral oscillations. And also there are pathological states in the brain like epilepsy or Parkinson, which we want to avoid. And there is ample literature. There are 2 excellent textbooks here from 2001 and from a recent one from 2018. But let me first of all illustrate what detrimental synchronization means for the London Millennium Bridge. This is what happened. And as the people were randomly streaming onto the bridge, as the time goes on and as the critical density of the crowd exceeds a certain threshold, which is marked here, then suddenly the system that starts to synchronize spontaneously. So this is self-synchronization. Here you see the order parameter, and here you see the wobbling amplitude, and you can see in the video the strong lateral oscillations when people started marching in pace with a bridge and the oscillations of the bridge were enforced. So this is what we want to avoid. Synchronization is an old field. Actually, 350 years ago already, Christian Huygens discovered that this happens if he put 2 pendulum clocks on this bar. So they were weakly coupled. And although they had slightly different frequency, they started to synchronizing after a short time. And this is an example from our times. If you can find it on YouTube. So if you take 5 metronomes and you put them on a bar, and all these metronomes have slightly different frequency. They have different, you can hear the sound, but if you put them onto a lateral bar and put this on these rolls so that they can move laterally, so the bar can move laterally, then what happens is, you can hear it already, the click of the synchronomes starts synchronizing, and after a short while, they are all going synchronously. So what about adaptive neuronal networks? I told you synchronization is important, sometimes wanted, sometimes unwanted in neuronal systems in the brain. And a very simple model, which is paradigmatic in the sense that it's the minimum model which you can use to describe coupled oscillators, is this model of phase oscillators where I labels the nodes from 1 to n, and we have the phases as a dynamic variable with some natural frequency of the ith oscillator and some coupling. Now, Aij describes the adjacency matrix, so the topological structure of the network. It's just 1 if there is a link and 0 if there's no link. And we have these coupling weights, k, kappa ij, and a coupling function which couples the ith oscillator with the jth oscillator. Now, in adaptive networks, these coupling weights are dynamic variables themselves, so they are governed by a dynamical equation. This is a relaxation dynamics with some small parameter epsilon, which marks the timescale separation of slow adaptivity of the weights and fast dynamics of the phases. And then we have this coupling function or adaptation function, which depends on the difference between the 2 phases. So the simplest example of this coupling function f is the Kuramoto phase oscillator, where it's just a sine function and you have an additional phase lag alpha, which accounts for the propagation delay between the nodes I and j. And here we have global coupling all-to-all with some coupling weights being adjusted by this equation. And here we have the adaptation function g, chosen as a sign, also with some coupling or plasticity parameter phase beta. Depending on how you choose beta, you can describe different adaptation rules. For example, Hebbian-like, which means in neuroscience, fire together, wire together. So the links are enhanced if simultaneous firing occurs. This is for phase difference 0, or the opposite anti-Hebbian rule if they are diminished, if the link weights are diminished in that case, or in between we have spike timing dependent plasticity, which means that it depends on which signal arrives first, whether you get positive or negative coupling. Now, so with this simple plasticity function, you can also get a wealth of synchronization phenomena. This was shown in work which we've done together with Vladimir Nikolkin, Vladimir Kazatkin, and Sergei Janchuk, and later with Rico Berner and Sergei Janchuk. In fact, this is the thesis of Rico Berner, which was published in the outstanding thesis, a series of Springer patterns of synchrony in complex networks of adaptively coupled oscillators. So what do we get? It's not only in-phase complete synchronization, what we get, but we get various states of partial synchronization patterns. In particular, in these adaptive networks, we get the formation, the emergence of hierarchical multi-frequency clusters. Here, the system, the whole system of 100 nodes, spontaneously splits into blocks of densely coupled subsystems. For example, we have one block here corresponding to this block in the adjacency matrix. And we have a second smaller block, which is also strongly coupled here. And we have a third block here up there. So the hierarchical ordering means that with increasing frequencies, the blocks become smaller, and there is strong coupling within and less coupling or almost no coupling in between the blocks. Within one block, you can either have a completely synchronized state or what we see here, a splay state where the oscillator phases are splayed out across along the unit circle. So if you look at the yellow ones, they correspond to one cluster, the green ones to one cluster, and the blue ones to one cluster. You see that all of them are splayed out. So effectively, we get an order parameter 0, but most importantly, the frequencies of these clusters are shown here in dependence on the label of the node. So we have the big frequency cluster here with the largest frequency, the next and the third and even the fourth one here in this plot. So you can get any number of clusters. Within each frequency cluster with fixed frequency, we have phase clusters. So this is a splay cluster. Ideally, the phases are splayed out. Here we have antipodal state where some nodes are here with the same phase and some are with a phase lag of pi. Or you can even get double antipodal. Here we have a phase lag of pi, so this is antiphase. And here we have another pair of antiphase clusters, but with a different phase angle, which can be determined, in fact. So this is work which we have recently done together with Rico Berner and Sergei Janchuk and some students, which you see here. This is a general phenomenon of partial synchronization, that you get very complex patterns. And one of these patterns, which I want to mention because a lot of work has been done during the last 10, 20 years, are chimeras. Now, this name goes back to the Chimera, which is a mythological monster. And here you see a particularly beautiful example on display in the National Archaeological Museum in Florence, dating from 800 before Christ. This is a mythological monster composed of incongruous parts. You see lion head, goat, and snake. And in complex networks, partial synchronization patterns are termed chimeras if they are self-organized splitting of the network into coexisting domains of synchronized and desynchronized domain. As you can see here in the pioneering work of Kuramoto and Batoktok, who discovered this theoretically, you have some nodes synchronized, fully synchronized in phase. These are phase snapshots as a function of the position of the oscillator. And you have some nodes which form a completely desynchronized phase. So the name was coined by Abrams and Strogatz, and a lot of work theoretically as well as also in the lab experimentally has been done within the last 10, 20 years. And there are some reviews and collections of reviews. So here I will concentrate on control of synchronization pattern, because this is important for power grids, for keeping power grids synchronized and stable. And there are various ways of control. For example, you can consider a multi-layer, a two-layer system where one layer consists of the power generators and the loads, and another layer consists of controls, so a communication layer. And you can have different topologies in this communication layer, for example, local or global coupling. And all of these are also coupled to the generators, so we can influence the generators. And basically one layer, the control layer, drives the other, the power grid and load layer. Also, you can modify the coupling. You can implement pacemakers into the grid, into the network. This is work which has been done by Giulia Ruzzene and Ralph Andrzejak and others. So one node drives the others. Or you can use adaptive topologies, which we will focus on, and generate some kind of hierarchical multi-frequency clusters. More practical kinds of control are, for example, known in the electrical engineering community as direct control, which is proportional to the frequency to stabilize the frequency, or proportional to the frequency difference, which is called frequency droop control. So you have a difference control, or you can use time delay as a means of control. A network by simple feedback, a simple feedback loop, you can modify or stabilize synchronization patterns. And this is interesting because delay in dynamics increases the dimension of a differential equation to infinity. Even if you have a simple first order single differential equation like this, and you add a delay term, this equation has infinitely many eigenmodes, and some of them can become stable, kind of them can become unstable. So you can produce very complex behavior by adding a simple delay term. And for example, you can induce instabilities, you can induce bifurcations, you can induce multistabilities, or on the contrary, you can stabilize unstable periodic or stationary states. And this is also done in networks with delayed coupling, but I will show you the simplest case, which was suggested almost 20 years, almost 30 years ago by Piraga's time-delayed feedback control of chaotic systems. So it's the field of chaos control, which means that we stabilize one unstable periodic orbit, which is embedded in the chaotic attractor, or fixed points can also be stabilized, or synchronization can be stabilized in networks. And if you look at a simple chaotic system, for example, the Rössler attractor, and you add time-delayed feedback in this form, difference of the delayed signal minus the non-instantaneous signal with some coupling constant, and if you choose the delay time equal to the period of one of the embedded unstable periodic orbits, you can actually stabilize this periodic orbit, and this is known as chaos control. And there is a whole handbook on this, and many papers have been written. So what we want to use is this delayed feedback control as one possible way of controlling synchronization in power grids. First of all, why is this topic of interest? Well, we are today in the process of a transition to renewable and sustainable energies, and we need stable and efficient operation of the power grid in spite of strongly fluctuating power input and also power output. But the wind and the solar energy are strongly fluctuating. So I think it is useful to adopt a complex networks perspective. This is a perspective or a view on power grids, which uses simple modeling approaches of the dynamics, for example, the simple swing equation, and focuses on the interplay of complex topologies and this simple phase oscillator dynamics. And the aim is, of course, control of synchronization and stability, to prevent cascading failures, and also to investigate the influence of stochastic fluctuations of generators and loads. So let me start with the German high voltage, ultra high voltage power grid. These are generators marked in green and loads marked in red, and the lines in between forms a complex network. There are data on the distribution of power of generators and loads. So here the loads are negative, have negative power, and the generators in green have positive power. And desired is to maintain a stable state of synchrony at a nominal frequency of 50 Hertz. And this is some work which we have done together with Simona Olmi and from Firenze, and Hal Gotthard, Ludmila Tumas, and Karl Totz. And I will present you a few ideas. First of all, the Kuramoto model of coupled phase oscillators with inertia. Now, before I have looked at the Kuramoto model without inertia, but with adaptivity. And here is the inertia term, which is added to the Kuramoto model in order to describe power generators, for example, synchronous machines, which have some inertia. This is the inertia moment II, and the nominal frequency of the grid is 50 Hertz. So we have this normalizing factor. It's well, this is all normalized here. And we have some dissipation parameter alpha. We have the power input and output. This is power consumption if it's negative, and it's power generation if it's positive. And there need to be some power balance to maintain a steady equilibrium. Then we have the coupling through the power lines, and this is the line transmission capacity K. And we have the adjacency matrix, which characterizes the topology of the grid. And we have this simple coupling function of the sine. Now, if we have perturbations of the frequency synchrony, we need to implement some control. And this is the type of time-delayed feedback control, which we have considered in this work here. And it just is the simple Piragas type control difference with some control gain, GI, and the feedback time or delay time, tau. Starting from the grid without control and looking at the characteristic of the frequency deviation. Now, this is the standard deviation of frequencies overall n nodes of the grid, and it's plotted here as a temporal average over time t. Time average is typically over 100 seconds, so it's a gliding time average. And here we have the line capacity, that transmission capacity in megawatts. And you see that upsweeping, we have some state of partial synchrony. So some are out of synchrony, and finally at large transmission capacity, we have this state of synchrony. Downsweep, we get this, so we have bistability of the system, and this is what we want to investigate, how we can control unwanted partial synchronization states. These are 3 examples, and you can see here a lot. This is the standard deviation of frequencies, time average versus the nodes. You can see many of them are in synchrony, but a lot of them are also out of synchrony. We have this solitary out of frequency, out of synchrony nodes. And here in this operating point, we have less, but we still have some 8 or 9 solitary nodes. And we have full synchrony, except for one single outlier here. It's also of interest to look at the stability properties. And this is done by looking at the largest Lyapunov exponent. So the largest Lyapunov exponent is positive in these states. It's an unstable state where it's 0. So this is not this is a stable state. But these states are unstable, and we can look at the Lyapunov vectors for each node and see which are the most important ones. Now, In the following, we will control only the solitary nodes. So what happens if we implement this time-delayed feedback control? Here we have 11 solitary nodes, and we look at the standard deviation overall nodes, and you see that initially the system is out of synchrony. So we have several ones, they are shown here, which are out of synchrony. They are in fact, the frequency is in fact oscillating, which is completely unwanted. But if we switch on control at this time here, and after a very short time of a few seconds, you can see that the grid returns to synchrony. So we get resynchronization, and this is also shown in the individual time traces. Well, it's the frequency as a function of time of these nodes here, which are out of synchrony. So we have been successful by controlling all solitary nodes. We don't have to control the other nodes, which are in synchrony, but can we do less? In fact, it is sufficient to control only a subset of nodes, not even all solitary nodes. And if we sort the solitary nodes in descending order of the Lyapunov vector, so the ones which are most unstable are first, so it's controlling 0 nodes, controlling 1 node, controlling 2, 4, 5, and so on, we see that this is the frequency deviation, standard deviation. We see that, let's look at the frequency and let's look at the stability. The stability are the orange symbols and the frequency deviation is the blue symbol. So regarding the stability, we can see that already one node, controlling one node can bring the, suppress the instability. So here we have stability. This is the 0 line for the largest Lyapunov exponent. And, but we need to control more to get back to synchrony. So we need to control, in fact, 8 nodes here, and then the system is back to synchrony as well, stability and synchrony. If we order the solitary nodes in descending order of the frequency deviation, it's similar. We need 1 node to suppress instability, and we need 9 nodes to bring the system back to synchrony. So in both cases, this is important. And of course, it's important to identify the solitary nodes. The importance of solitary nodes in power grids has also been pointed out in this paper by Hellman and co-authors, who looked at who analyzed the power grid dynamics. Now, this is a very simple model. So the question is, if we add the voltage dynamics, this is the next what we can do to make the model more realistic. And this has been done by Katrin Schmiedendorf, Jochen Peinke, Friedrich, and Kamps. Then we get an additional dynamic equation for the voltage amplitude. So we have sort of phase amplitude coupling here. And we can also add time-delayed feedback to the phase dynamics as before, and it works as well. So you can see the frequency deviations are brought down. So here we have controlled the solitary nodes, and this works as well. And also it works for other grids. Here we have used the Italian power grid, and you can see this has a very different topology with loads, red, and power stations, power generators, green. And also the characteristic here, we have chosen this intermediate operating point, which is characterized, well, here we have complete asynchrony. Here we have complete synchrony, except for one node. If you look closely, this is the last node in Sicily, which is the dead end. But here we have quite a few, in fact, 20 nodes, which are out of synchrony. They form these 2 clusters, and also some solitary nodes, 7 solitary nodes. So what happens if we control those solitary nodes, or even a subset of those solitary nodes? Similarly as before, we see that it's sufficient to control one node, one solitary node, to bring the system back to synchrony. And we need, in fact, 2, 3 nodes to control, to bring the system back to synchrony. And, well, 2 nodes to bring the system back to stability and synchrony. And similarly for the other ordering. So now that we have seen how adaptive neuronal networks can be described and how we have seen that power grids can be described with chromotor model with inertia, is there a connection between the two? Is there a relation between the two? And this is surprising and it's interesting because we can write an adaptive network of chromotor phase oscillators, which I introduced earlier with this coupling function and adaptivity function with adaptive coupling weights kappa. We can actually write this as a first order equation. This is, as a second order equation of a single variable phi. And then we have this, we can either look at the system of first order equations or the single equation of second order. Here, I want to draw the connection with adaptive networks. So I take this form and we can write this form. Well, first of all, the chromotor model with inertia can be written as a second order system with two variables and first order derivatives, just by introducing this frequency deviation from the nominal frequency omega I, psi I as an additional variable. So this is the standard procedure to transform that second order differential equation into two first order equations. And you see we have this coupling function. It's not yet the form of the adaptive neuronal network which we want. But if we split this frequency deviation according to the links, this is the adjacency matrix, into the different components for each link from J to I, we get pseudo coupling weights, chi ij. And for these pseudo coupling weights, if you insert this, we have, first of all, we have a form which has the coupling now in the first variable, and for the pseudo coupling weights, we get a dynamics which is very similar to that of the adaptive neuronal networks. In fact, just this function G is now minus h over gamma. And here in the first variable, we have the coupling function, but it is different. The coupling function F, which is here, is identically equal to 1. So the power grids chromotor model with inertia form a subclass of all adaptive networks. And but still, this is an adaptive neuronal network with some pseudo-adaptive coupling weight. And we can use the results from adaptive neuronal networks, for example, multi-frequency clusters. And here for the power grid model, we get, for example, multi-frequency clusters. Here we have the mean frequency, one cluster, a second smaller, a third even smaller, a fourth even smaller. And the phases, you can see these are in phase clusters. So the first frequency cluster is in phase. It is the adjacency matrix is homogeneously blue, but there is little coupling between the first one and all the others. But intra-coupling is strong, again, in the second cluster, in the third cluster, and in the fourth cluster. So this is an example of a 4-cluster state of in-phase synchronous clusters. For other parameters, here we have a different topology known locally coupled ring topology. We get two clusters, one big coherent cluster and one small cluster consisting of 3 solitary states with the same frequency. These are the phases and the adjacency matrix. Now you can see the splay characteristic of the big cluster. It's a splay cluster. It's not in phase. And these lines, these 3 lines, which are sort of much less coupled to the rest, correspond to the solitary states. So what does this mean for power grids? Now, we have identified the pseudo coupling weights chi, j, I of the adaptive neuronal network, or the adaptive network in general. We have identified this with a power flow from node J to node I. So what can we say about the average power flow? The power flow is, of course, here it's chi ij versus time. It can oscillate. This is not what we want in power grids. This is an oscillating power flow, and we can see the average power flow is here. There are some main lines, and the solitary nodes are marked by these blue squares. And you can see if we don't look at the average power flow, average over time, but we look at the spread of the oscillation amplitude, which is the maximum of the power flow minus the minimum power flow for line ij, then we get a picture where the lines on which the power flow fluctuates strongly are thick and dark gray. We have, for example, this line. This is a solitary node in the Leipzig area. And we see that here we have really some lines with strongly fluctuating power flows. And this is critical. So if we need to control, we need to control those lines, and we need to be careful and cautious about those. By the way, coupling between non-solitary nodes is practically constant in time, so it's not fluctuating. So these are the solitary nodes which make the trouble. They are the troublemakers, and we have to be careful in controlling them. So what about if we expand the model and also take voltage dynamics, as I showed you before? This is the voltage dynamics equation. Then we get, again, an adaptive. We can write this in the form of an adaptive neuronal networks. You know the first two lines already, and now we have a third line. And this is the third line, which comes from the voltage dynamics. And what you see and what is interesting is that this is also known in neuroscience. In neuroscience, people have discovered this and called it metaplasticity. So it's another plasticity. Here we have the coupling weights, which are adaptive, and here we have an additional variable, which is also adaptive. This is in the neuroscience literature. In this review, it's known, and we have also described it in our paper. So I'm coming to the end, and I hope I have given you some perspective of complex networks and how they describe the intricate and delicate interplay of dynamics and network topology. And this is important for complex real-world network topologies like the power grids. We have simple dynamics of phase oscillators, or even amplitude phase, but even pure phase oscillators already show us that there is this intricate interplay. And the Kuromoto model with inertia is a subclass of adaptive networks. This is a novel view of this, and we can learn from neural systems, for example, that there is a possibility of hierarchical cluster synchronization. Of course, we want to avoid this in power grids, but first we have to know what is possible and when does it occur in order to take measures to prevent it. I have also shown you some novel concepts for power grids, for power grid control, namely this dynamic. Well, I haven't shown it here, but it's also in one of the publications which I showed you. We can look at a dynamic two-layer power grid network, where the second layer is the control layer, and it's also dynamic. What I have shown you is delayed feedback control as a way of controlling power grids. And also, I think partial synchronization patterns are important for the onset of instabilities. Although we want to avoid them, we have to know them. And they are, for example, solitary states or multi-frequency cluster states. So let me finally thank my collaborators and co-workers, in particular, Jakub Sawicki, Rico Berner, Sergej Janczuk, and Vladimir Nikolkin, and also some students, Max Thiele, Karl Totz, who have worked with us. In particular, I want to thank Simona Olmi, who has been vital in this work, and Ludmila Tumas, Hal Gutar, some students, and Volker Mehrmann from Maths at TU Berlin, and also Yuri Maestrenko, Ralf Andrzejak, Julia Ruzzene, and many others. And thank you for listening.
Thank you, Eckehard. Thank you. Thank you for this wonderful talk. So usually we leave the time for just a couple of questions, and then we immediately start with the other talk. So I ask the audience if there is some questions for Eckehard, or otherwise we postpone to when we have heard also from Florian. So not able to see the chat. Fabio, do you see someone who wants to speak?
No, nobody is writing anything in the chat, neither here nor in YouTube.
Okay. So I will suggest to go ahead with the other talk that will be introduced by Piero. So I leave to him the floor and mute my micro.
Thank you, Mattia. So I'm going to introduce Florian Dörfler. So Florian is a professor at the Automatic Control Laboratory at the ETH Zurich and deputy head of the Department of Information Technology and Electrical Engineering. And his research focuses on mainly on distributed control and optimization in complex systems. And he has been looking at very diverse applications, including smart power grids, robotic coordination, social networks. So more generally, we could say that his research has been devoted to bring together nice mathematically principled theories with applications. And so regarding the topic of the talk he's giving today, so Florian has been, as you probably all know, one of the pioneers that first applies the methodologies of control theory to problems in the field of power grids. And so I leave to him the virtual floor to give us his take on the control methods for low-inertia power systems.
Perfect. Thank you very much for the kind introduction, and hello everybody out there in the cyberspace. Let me jump right into the topic. So low-inertia power systems are essentially quote-unquote future power systems, which are not based anymore on mechanical inertia. So the last talk gave us very nice course dynamics model of how inertial generators interact with another. As will turn out, future power systems may have less inertia, and so the models will slightly change. And of course, interesting question would be then how to adapt the various models we've seen for future grids. Very well. So I'd like to acknowledge just a few collaborators. There's too many to mention, but in particular, my former postdocs, Marcello and Dominic, as well as PhD students Ali and Irina, and a whole bunch of others that helped me along the way. So there is quite a revolution going on in the power system, and it's not what you think it is. So at least most people think it is. So when you ask a random person in the street what has changed in the power system, then you'll probably hear, well, we go from fuel-based and non-sustainable generation to renewables, which is sustainable. Yes, this is correct, but that's not really changing anything about the core of the power system. If you ask maybe a more informed person, so the typical scientist, say in my field or so, or probably also in this audience, you'll say, well, now we have much more fluctuations and variability. Generation is now distributed. You replace one nuclear plant by tens of thousands of solar panels. And so this is certainly true. You go from distributed and variable, from central and dispatchable to distributed and variable generation. But again, that's not really changing the core of the power system. What is the core of the system? It's actually going back a couple years, more than 100 years, to these two people. You may probably know them. Let's call them Mr. AC and Mr. DC. And as you may know, after Mr. AC, aka Tesla, won the war of currents, the core of the power system was based on the concept of a synchronous machine. That is, there's a big chunk of iron rotating a magnetic field that will produce alternating currents, okay, which induces inherent electromechanical coupling, which among others causes all the synchronization that we've seen in the last talk. Now, future power systems will not be based on rotational electromechanical power conversion, but just based on power electronics. So renewables are interface with power electronics, just a bunch of devices that switch on the megahertz timescale between sort of 0, 1 on and off, and thus produce a current waveform. Okay, and there's no physics to that, it's just purely digital control. So traditional power system had essentially the large rotational inertia as a buffer. It's literally a big flywheel which would absorb all sorts of fluctuation, generation, load imbalances or faults or whatsoever. And that's really what keeps the power system stable as it is, what keeps it robust, what keeps it resilient. Future power systems based on these power electronic devices have no inherent energy storage aside from a few, negligible capacitors here and there. So there's no buffer whatsoever. As we heard in the last talk, synchronous machines are actually called synchronous machines because they're synchronized, right? Of course, not globally, but within a rather large operation range, there's a very stable, robust purely physical synchronization mechanism, just based on clever design dating back to Tesla. Whereas power electronics themselves, they don't do anything unless you control them to do so. So there's no inherent self-synchronization, no stability whatsoever, just based on physics. So you need to reproduce that by means of control. For synchronous machine, we know very well how to do control of voltage and frequency. We know how to survive blackouts and large disturbances. For power electronics, actually, we don't do this. So here control is actually very fragile. There's various examples. I'll later tell you a few. What's the only plus we have here on the future power system side? Well, power converters are very agile control system, very fast control system, very modular. Essentially, you can do almost anything with power converters. Whereas synchronous machines have very slow actuation, slow control, meaning, you know, on the order of seconds of actuation time, where most interesting dynamics happens in milliseconds for power converters. All right, and so now we have to leverage this nice control architecture here to overcome all the cons of the future power conversion mechanisms. So these concerns are not hypothetical. I'm not over dramatizing. There's quite a few blackouts by now in recent history in the last 10 years that can be attributed to these so-called low inertia power systems, that power systems do not have sufficient mechanical inertia, not have sufficiently many synchronous machines. For instance, one of them was in Australia. I actually went to Australia shortly afterwards. It was in 2016. If you read the post-mortem report for blackout, you really see that there was a lack of robust control. In this case, you know, the wind farms that were on the grid, that were to a large extent providing the generation, but also the voltage control, could not tolerate disturbances and essentially turned off. If you talk in person to the operators, or if you read the report between the lines, you'll actually see that a conventional power system would have been resilient. It would have easily survived these faults, but these low inertia type power systems did not. And, you know, this has been broadly picked up by, you know, transmission system operators, manufacturers, funding agencies. You know, there's not, you know, by now this is quite a mainstream problem. I guess back in 2015 or so, people were not fully aware of this yet, but now this is sort of the core problem in power system dynamics and control. Just to show you how desperate this situation is, my favorite example is actually from Germany, where they decommissioned a nuclear power plant. But what they did, they kept the mechanical rotor on spinning as a flywheel to provide voltage and frequency stabilization, which they couldn't provide otherwise. Okay, so they literally, you know, decommissioned the entire nuclear reactor, but just kept the flywheel on, which of course not a very economic solution, as you can imagine. There's other solutions. You probably heard about Elon establishing his big batteries all around the world, and more in Australia to counteract another such blackout. So they have now a bunch of Tesla batteries that very quickly provide control in case of some sort of frequency disturbance. It turns out these batteries are often successful, but not always. Actually, there was another blackout, which was really triggered by very aggressive control of these batteries or the power electronics involved there. So the overall picture I want to paint here is really that what I regard as the main technological obstacle towards building a sustainable power system is how can you robustly integrate power electronics into the power grid? How can you run a power grid maybe with only 10% of synchronous generation and the rest is all power electronics based? And it's not only me, I think that's the broad viewpoint by all the system operators, device manufacturers, and so on. The power system community, where I'm not an insider there, I'm more an outsider, is very quick jumping on such problems and is very organized. So I was invited to a task force of that community together with a bunch of power system experts to really think about what are the issues, what are the challenges, what are the problems to be solved, and we should provide a tutorial and survey on that. And our conclusion was, you really have to rewrite the models. Swing equation models and so on are not appropriate anymore for the future systems of very little inertia. You need to redevelop the stability theory. There's a quite rich stability theory for power systems based on synchronous machine, but not for the future ones. Novel computational tools, just because now you have to go down much lower in the timescales. And of course, new control methods. Essentially, you should revisit all of modeling, analysis, and control. And for me, the key unresolved challenge was how can you control power converters, in particular so-called grid-forming power converters, in a robust way? I'll tell you what grid forming means, but it literally means synchronizing power converters that would spontaneously synchronize with another, to use the language of complex systems. And what's very nice about this problem, it's not a purely academic problem. Industry is really willing to listen because they don't have an off-the-shelf solution to these problems. And so it's a quite nice problem to get into action also with people, and they would put it into the field if they're convinced by your approach. So there's sort of three communities involved in this domain for the most part, which is on the one hand, power systems, on the other hand, power electronics. And what I found quite surprising when I got into this, that, you know, you would think they're close, but they're not. They typically don't talk to each other. So power systems abstract power electronics often as a controllable voltage source and vice versa. For power electronics, the power system is often just a stiff grid. And what I found very often that the control engineers are the ones that have to provide the lingua franca, sort of the intersection, how these two communities interact. And they also have very different standards. So these care about experimental validations. These care about system level stability type studies, either theoretical or computational, whereas control system people typically care about theories of proving epsilons and deltas. And so all the methods that I present today, I selected only those that meet the standards for all three communities. That is, behind every method, there will be a hardware experiment, a theorem and a proof, and also grid simulations. Okay, so I want to make sure that all of these are solid. Good. What will I talk now? So after this introduction to low inertia power system, I want to explain to you some of the modeling and how the modeling changes and what are the new specifications. Then I'll present you some of the state-of-the-art grid forming controllers and discuss the pros and cons, and eventually, you know, conclude with a comparison and some future avenues for work. Okay, let's go into the modeling with specifications. So if you need to go a few levels lower in the details, then typically you need to go really down to the circuit level, because many of the interesting power electronics problems happen on that circuit level. So the signals, if you were to measure, you know, the current at the plug in the wall, it would be a three-phase signals, meaning it's a superposition of three periodic signals. So these are typically labeled A, B, and C. So it's a three-dimensional vector. And all of these have zero average. Okay, it could be something like 3 or 1 sinusoid and 2 distorted sinusoids, maybe slightly phase shifted. Okay, the signals you typically measure are not so general. They have one further property, namely they're balanced. And there's various hardware equipment in the grid to make sure this is the case. What does balance mean? The sum of the three signals is 0. Okay, and that's a very good assumption to make. It holds true, you know, with 99% of the time, or in the most of the frequency domain, meaning that the signals all essentially have the same amplitude and they're all phase shifted by 2 pi over 3. Okay, so it could be something like this, something very complex, but all by 2 pi over 3 phase shifted. The signals that typically would like to see is these three signals being nice sinusoids, meaning the amplitude is, in this case, a constant one, and the angle is a constant one with a constant synchronous frequency. So you want to have three nicely synchronized sinusoids with the same amplitude and phase shifted by 2 pi over 3. Okay, so that's the goal. That's what, you know, you would refer to as synchronization if you converge such a signal. So it's a good assumption to make that everything is balanced. That is, you know, the three signals sum to 0, meaning you can just work in two-dimensional coordinates, and that's probably what all of you have seen in your whatever bachelor studies, for instance, because when you model circuit, you normally work with complex numbers. So you would probably only work with the amplitude and the angle. Okay, so you work with something like this. So that's sort of in polar coordinates, or you can work with it in Euclidean coordinates, but, you know, it's just a two-dimensional signal at the end. And what is power? So in power systems, people typically don't work with currents and voltage. They work with signals that are active and reactive power. Active power is just the inner product of voltage and current. So you take this vector for current and voltage, you do it in a product, and reactive power will be this skew symmetric inner product where you have this skew symmetric matrix in between. So, okay, so much about basic language and modeling. Now, what is a synchronous generator? We've just heard the swing equation, and the swing equation is roughly this here. If you make some assumptions, you get from this to the swing equation. I want to get one slight level deeper, so let me use the language of energy conversion, so Hamiltonian type systems. So what we have here is one energy storage device, which essentially is the flywheel, the rotor of the generator, that is driven by an exogenous torque, maybe has some viscous damping. So these are these equations, just the Newtonian equations. The connection to the grid is through what is called the stator. And here just write the change of flux. So the inductance times the change of current as a resistor and the grid voltage. And now everything that's interesting is in here. And what is in here? It is the rotating magnetic field. Okay, and the rotating magnetic field has this inductance matrix. And from this one, you can work out what is the torque that this rotating magnetic field produces, which is this term. And maybe now with the sign here, you probably recognize the swing equation. And what is the voltage that it produces? It's this term. Okay, and these are really the two terms that make the magic. That's why power systems synchronize, because that will introduce the sinusoidal diffusive type coupling, these terms. So this is really clever physical design. Okay? So it's electromagnetic rotating energy that makes everything synchronized. Now, what is the equation for a power converter? So in this case, a particular topology of a converter, but it applies to many different variations. So also there's an energy storage element on the DC side, which is just a capacitor. And there will be some DC current entering that could come from, say, a wind turbine, a solar panel, or whatsoever. In the connection to the grid, there's a filter. Okay, there's a bunch of switches in between that produce like a ripple type signal. And to smoothen that signal off, you have a filter here. And so you have this filter equation for the grid. And what is in between? In between are the switches. Okay. And if you don't work on the time scale, say, of nanoseconds, it's quite a useful abstraction then to model the switches as a continuous signal. So you use some averaging techniques. And you say, well, this signal here is 1/2 times the DC voltage. This signal here is 1/2 times the DC voltage. So the voltage that you can produce here can vary as m times DC voltage, where m can vary between plus and minus 1/2. Of course, in both coordinates. Yeah. Remember, we have two-dimensional coordinates for this power system. Likewise, the current that comes over here is the AC current multiplied by this vector m, which can vary between plus and minus 1/2. So this is sort of the continuous abstraction of the switches, which is a very good assumption if you work with the millisecond timescales and higher. Meaning this is now the coupling between the DC side and the AC side. Very well, let's put these two models side by side. And you can see these equations are actually not all that different. If you abstract a little bit, maybe some of you are familiar with the language of bond graphs or Port-Hamiltonian type systems, then you will typically think about these as follows. Both these models have as the starting point an energy storage, right? Which is the mass or the DC side capacitance. Okay, the main difference, the mass is huge. This is nearly negligible in terms of energy storage. They both have some exogenous energy supply, which is either the torque coming, say, from a steam turbine, or here the DC current. Main difference, the DC current, you can actuate extremely fast, again, milliseconds or lower, whereas the torque is very slow to modify on the order of seconds. And then there's the energy conversion from, in this case, sort of the DC to AC, or you can also think about mechanical power as DC and here AC. And the energy conversion on the one hand through the rotating magnetic field, so purely physical, based on clever physical design, or through the switches, namely this signal M, that you can entirely control. Okay, so the one energy conversion is by physics, the other one is by control. And then the connection to the grid here is sort of the same for both. It's more or less the same type of equation. The main difference being for the synchronous machine, this connection is very resilient. That is, you can overload a synchronous machine. You can survive a large fault and go through a whole bunch of nonlinear dynamics. You can overload it by a factor 6 to 10. For a converter, you cannot overload any of that because you would just burn all the switches. Meaning this connection here has to be very, very tightly controlled. Otherwise, you just fry your converter. So on that abstract sort of energy type level modeling, the main difference is that they're both energy storage and conversion mechanisms, where one is physical and robust, but the other one is controlled and agile. Okay. This one has a huge storage. This one has essentially no storage. Good. So what are the control objectives? So you want now to have a network of converters, or maybe converters into dream. You want to control these converters. That is, you want to now control these switches so that something good happens. What do I mean by good? It's, as in the previous talk, it means synchronization. Okay, what do you want? Synchronization in this, again, remind you, we use these two-dimensional coordinates to describe all voltage and current. So in these two-dimensional coordinates, you want everything to synchronize on sinusoids of the right frequency. So all the voltages at all the nodes K should obey asymptotically such a differential equation, which, as you can see, models just a harmonic oscillator at a frequency omega star. Additionally, you want all voltage amplitudes to have certain set point values. So, for instance, Vk star is the reference value. And you would like to have the power at the terminals of the converter, the active power and the reactive power, which are, again, inner product of voltage and current, and the skew symmetric inner product. You want these to follow particular set points that you're given. So this is, of course, a non-linear specification, depends on the products of the variables. You can actually work also now in angle coordinates and make this a linear specification. Namely, you could just say there's a, you want any voltage in node K to be related to any voltage in node J through a rotation matrix, okay, which is very much along the lines of the previous talk, where there were these sign of the angle difference type variables, okay. Essentially means given any two voltages in the grid, there's a rotation matrix in between, and there's a one-to-one conversion between these two objectives. One is local but not linear. This is linear but global. So you choose what you want to work with. Going more into maybe to the language that you're used to. So you can think about the control objective for a power system to be essentially a bunch of coupled oscillators. So a bunch of guys that run around the cycle, just like the Kuromoto oscillators that we've seen in the last talk. You want them to be all synchronized, so they should all run around with the same speed. That's given by this differential equation here. They should have all the desired amplitude that you give them, different for each of them. And you want to have certain desired relative angles because that corresponds to your power injections that you want to have. So you'd like to stabilize the system to this type of solution. On top of this, so this is just the stationary objective, you want some dynamic objectives. One is, a power system is never at equilibrium. There will always be fluctuation disturbances, so you're best nearby an equilibrium. So what you want to have nearby is, if you're not at the right frequency, but your frequency slightly deviates from the set point, then you also want the active power to deviate from a certain set point with some proportional constant K. So there should be a desired sensitivity, sort of d omega dp, if you're not at a steady state. This is called droop control, also alluded to in the last task. Often you just code up this equation for a controller. It says if your frequency deviates, then your power should also deviate accordingly, according to some specified sensitivity. And there's similar type of objectives for voltage, amplitude, and reactive power. Moreover, you want this to happen grid forming. What does grid forming mean? I guess in the language of complex networks, it means spontaneous synchronization. You don't want to track any exogenous pacemaker. Like, of course, you could just send everybody the desired frequency, please track it, using, for instance, a GPS signal. No, you don't want that. You want this omega star to emerge really spontaneously if you want. So they should find omega star by essentially averaging, okay? By diffusive coupling. Finally, you want to, most importantly, survive disturbances. Okay, so there are many faults going on. I said in traditional power grid, what keeps you safe from these faults is the rotational inertia, which is a big buffer, big low-pass filter. You don't have this in renewables. So you want to survive these faults, and you have very tight constraints on your currents, meaning you cannot fry the switches of the converter. Okay, so this is what you'd like to have. Now that sounds like a quite challenging control problem, I should say. And it is challenging. So let's maybe see what is out there. What have people proposed to solve this type of problem? Let me walk you through some state-of-the-art approaches, some maybe a little bit closer to what you think, and others a little bit further away. So the baseline solution is sort of the naive one. Let's just use all our nice batteries, supercapacitors, flywheel, whatsoever, to emulate what is called virtual inertia or synthetic inertia or virtual synchronous machines. Essentially, let's try to make a power converter plus an energy storage device in closed loop, make it look like as if it was a synchronous machine. Can you do this? Yes, there's various papers showing you how to do it. There's various demonstration studies, so it can be done. Let me maybe quickly tell you how to do it. I don't want to go into all the details of the control design, power converters, because that's not your expertise. Probably that's not what you care about. So let me illustrate it to you on a cartoon level. How would you make a power converter look as if it was a synchronous generator? So what you do is you take measurements of current and voltage for instance, using some sort of tracking device like a phase-lock loop, process them, low-pass filter, and so on. And then you have an internal model, say a model of a synchronous machine coded up on your microcontroller. And you feed this internal simulation model these measurements and wonder, okay, how would a synchronous machine now react if you had this particular terminal signals, this terminal voltage current? And you get what a synchronous machine would do. Well, then you get the signal, what would a synchronous machine do? And then the task of the control designer is, well, let's make sure the power converter will produce exactly this particular signal. So use some sort of tracking controllers to make sure this is going to happen. And then you modulate the switches so that the power converter behaves as if it was a synchronous machine based on the internal simulation model. The assumption is, of course, you can do this. That is, you have enough internal energy to emulate a synchronous machine, to pretend as if you were one. And the assumption is that you don't have any constraints to encounter, meaning a synchronous machine after a fault would respond to having a big current spike. Well, the converter cannot do this, right? If you have that big current spike here, you will fry the switch. But, you know, it's an assumption. Moreover, you control the energy balance across the converter using sort of your DC inputs, or using, for instance, a solar panel or a battery behind the converter. So you just do essentially energy balancing with the DC side control. Okay. And the assumption is that if you have unlimited power and you can do this almost instantaneously to perfectly balance the energy across the converter, is a good assumption. Well, not really. You know, if you respond by very aggressively sending out power into the grid, you may deplete the voltage of the capacitor and you've lost. Okay, so this needs to be extremely fast. Okay, so this is sort of my cartoon of how you control a power converter, and you can see there's various things that can go wrong. So let's think about it. Can you make this work? Honestly, no. And if you look at all the people that made it work, you'll see they used a lot of hacks. Essentially to use a whole bunch of artificial dissipation into the system to make it work. Okay, dissipation meaning you add something like a virtual type of resistance. You mimic a resistor in digital control. You maybe add a bunch of low-pass filters. You put in limiters, dead zone blocks, switching logic, and I don't know what all sorts of things to make it work. Long story short, it does not work, but with enough hacks, you can make it look as if it works. So this idea of having a virtual inertia, a virtual synchronous machine, essentially is use your converter to emulate a flywheel. Okay, so you track the model for synchronous machine and say, in closed loop, I want my converter to look as if it was a synchronous machine. So I want to mimic this physics of the synchronous machine, like the inertia, for instance. It's sort of a commonly accepted solution because the selling point is always, oh, it's backward compatible. If everybody to the outside world looks like a synchronous machine, then nothing changes. Yeah, sort of, not quite. It turns out if you really want to make this work, you need a whole bunch of tricks, I told you. Essentially, to introduce enough dissipation to the system, you need to have enough instantaneous energy storage available. And as I told you, the power converter here and the synchronous machine are conceptually similar. There's both energy conversion devices, but very different characteristics. Essentially, you have a device that has essentially no energy storage, but is very fast. And you want to mimic a device that it has a lot of storage and is very slow. Essentially, you want to drive a Ferrari like a truck. Well, why would you? And yes, it will certainly go wrong. Okay. So typically, it's just a poor fit. So they have very different type of storage and actuation. This works well in this, what some people call the small signal regime, maybe using more math language, sort of in the regime where linearization performs well, so near an operating point, but performs very poorly when you go to the truly nonlinear regime, far away from the operating point, so certainly after faults, that's where you want it. And of course, the question is, why would you use such a huge over-parameterized solution? Why do you want the converter to look like a synchronous machine? And of course, you will ignore the limit and you'll fry the switches. So it's at best something that works in a lab, but not in reality. You can make up your own opinion about this. Some people love this concept, some hate it. It's a little bit controversial. I personally don't believe in it. There are simpler solutions. And let me present to you one solution that's based, again, on bachelor physics. Namely, it uses the duality of mechanics and electric circuits. So recall that this is the generator with this equation, and this is the converter with these equations. And now recall from from mechanics, the dual of the mass is the capacitance, meaning these two equations more or less serve the same purpose. I mean, these already look the same, the lower two for the inductor. But, you know, if you were not to think of the mass as the capacitor, then these equations look very similar, especially since you can choose the m. I mean, you could literally choose the m to be this term, or would you? Let's think about it. Let's reparameterize our control input. It's a two-dimensional vector, so I can parameterize it amplitude and phase. Okay, so I call my m now an m amplitude times an angle, where the angle can be actuated. So you can control the amplitude and the frequency. Okay, so add an extra equation for the angle, and I can control the frequency of the angle, and I can control the amplitude here. And now you should realize that literally these two models are almost identical already without doing any control. If you want to mimic the rotating magnetic field, you want to mimic this term, well, you already have this term more or less. The only thing you need to make sure is that the angle, or the root of the angle, which is the frequency, sort of follows the same law. So the dual of the frequency is the DC voltage, meaning it makes sense to control the switching frequency as the DC voltage. Okay, so you just say the switching frequency is the DC voltage times a constant, and the constant just makes sure that the units are right, nothing more. And now you virtually one-to-one equivalence the two models. Okay, and you didn't do anything other than leveraging the duality of circuits and mechanics here. So essentially what we say, you know, these equations are now structurally equivalent. So the DC capacitance essentially is your inertia. And, you know, they are structurally equivalent. The mathematical structure is the same. Of course, there's a major difference in parameter, meaning that the DC capacitance essentially is negligible, whereas the inertia is, of course, huge. But now you have reconstructed the same equation. And if you really care about inertia, then just get a bigger DC type storage element. Okay. So now we really have the structural similarities. I mean, all the states are the same. The frequency essentially is the DC voltage. And now you can one-to-one get the same equations. Does this work? This is a very simple idea. Yes, it works. You can just implement it as it is. So here's something we've done in our lab, and some other people across the world have now reproduced it a few times. So you just control, you pretend your switching frequency essentially is the DC voltage, and that would work very nicely and very robustly. You could nicely track some power set points, produce nice sinusoids and all these things. It's very robust. It's very hard to destabilize it. Okay, so it works very well. So maybe that's a more clever way of how to implement that synchronous machine. I want to go back to something that's been mentioned in the previous talk, namely another type of control is this proportional droop control. And that is, you want to mimic this proportional trade-off of the frequency variation in active power. For instance, you say, I control the active power as a set point plus, you know, a deviation in frequency. Okay, and that's what everybody's doing. That's the traditional control, dating back in power electronics to 93, in power systems to the 40s, so quite a while. Okay, you can do something similar for the voltage control, of course. Now, does this work? So essentially now the reference for your controls for the power converter are essentially mimicking the droop control from synchronous generators, and the voltage control, which essentially also this proportional trade-off in the voltage and reactive power errors. This works, but essentially what you do here, you control the frequency with the active power and the voltage of the reactive power, and you essentially assume that these are independent signals. So P and omega are coupled and Q and V are coupled. But that's not true. That's only true near a steady state that, say, the active power is independent of the voltage magnitude, okay? So as soon as you go away from the steady state, or if you have big loss in the system, that's not true. Again, it requires many tricks in implementation, similar to the synchronous machine or virtual synchronous machine. It performs very well near steady state, but it does not perform very well in the large transient regime. So what power people call the large signal behavior. So it has a very narrow reach of attraction, which is not surprising because you close two linear control loops, linear single input, single output, SICC, single input, single output, for a system that's inherently nonlinear and coupled, multivariable, multi-input, multi-output, and thus unsurprisingly performs poorly in this large signal regime. Okay, but that's a baseline control. That's, you know, the second most popular that people use. There's a better version of it, which goes back to virtual oscillators or oscillator type controllers, so phase oscillators, similar to what we've seen in the last talk. So the idea is here, can we control a converter essentially as a nonlinear oscillator? For instance, maybe some of you are familiar with things like a van der Pol type oscillator, which has a circuit realization as follows. So it's an LC tank that gives you sinusoidal oscillation. And then you have a nonlinear resistor here, maybe a resistor which has this characteristic. So it has a positive resistance near the origin, negative globally. And this will give you a very nice, robust oscillation. It's called a relaxation oscillator in nonlinear dynamics. And now you control every converter to look like this, and then you connect them all. So there's a current interfacing with the grid. And what you get is actually very nice properties, like almost global stability properties, to be mathematically precise, where you nicely converge to the desired waveform in current voltage space. Essentially, this was mostly proposed by Brian Johnson and Sarah Stoppel in 2013. And simplified model you can analyze. You can prove many nice properties. So locally, this would reduce droop control. You can prove almost global synchronization properties when they're all coupled and so on. In practice, this is proven very robust. But boy, it's really hard to control these things. They would synchronize, but they would synchronize to something that you don't want, right? So they are too robust for their own good, and they can't really be controlled. When I say, please synchronize, but to this amplitude, and with this relative phase angles and so on, it's very hard to do this for nonlinear relaxation oscillators, okay? So to some extent, this idea was a dead end until, say, 3 or 4 years ago, when people came up with what is called the dispatchable virtual oscillator control, meaning more controlled version. And this is the last control concept I want to introduce to you. And that's really very much resonating now, again, with the previous talk. You control a power converter as if it was a nonlinear oscillator. That is, you want to control these oscillators so that they all synchronize the solution with particular frequency. They all have desired relative different angles, and they all have a certain amplitude. Now, how would you construct that type of synchronizing signals? Well, one way is to go essentially to, I guess, what is called artificial potential functions. So you wonder what is, for instance, a mechanical realization of this particular nice behavior. It would be something as follows. We have a bunch of guys that run around the ring with particular frequencies, and they have some springs attached to them that would stabilize the amplitude, and they have another spring which gives you the right relative angle. Now, if you were to translate this mechanical system into a differential equation, it would look as follows. So the change of the voltage, which describes the position of one of the oscillator, would be that rotation matrix that gives you this particular force here. Then these springs for the right amplitude will give you this term here. So essentially it's amplitude squared minus desired amplitude squared times the voltage. And then there's this spring, which is 0 if they have the desired relative angle, meaning there's a bunch of potential forces that say the force between converter J and converter K is 0 if they have the desired relative angles, with some, say, spring coefficient, and then you sum of all of them. So that gives you the synchronization. Probably you can convince yourself that this type of differential equation would, from almost all initial conditions, so with probability 1 in the phase space, converge to this solution. And yes, you can mathematically prove that. The question is, how would you ever realize this with a power converter? I mean, you don't have any of the relative angles. Only decentralized control is allowed. It has to be in the milliseconds. And so surprisingly, you can realize this. And namely, what is the complicated term here? It's how to construct this relative angle potential force here, which gives you this sort of coupling. And you need to leverage the physics of the system. And you probably find that, I can explain it later if you want, that if you measure the local current and then use Kirchhoff's laws, that measurement of the local current gives you the diffusive interaction, and that gives you more or less this type of term. Meaning, by using just the local current measurement and having a particular control in the local voltage, you can exactly reproduce these desired spring forces and make them synchronize. When you write all of these equations in polar coordinates, you get actually exactly a droop control back that people looked at before. Droop a little bit non-linear, so divided by voltage squared, but if you linearize it for voltage equal to 1, so in a particular normalized system, you get exact droop control. Same for the amplitude, I will skip that. And you can actually show for quite high level and detailed power converter models. So every model has, say, 5, 6 state dimensions. that this would get you almost global stability, that these nonlinear oscillators would actually converge to the desired solution, provided that your network connectivity is sufficiently high compared to the power transfers, and it turns the need to control the amplitude slower than synchronization. Okay, so meaning essentially this control again has to be slower than that. Okay, and again, I could go into details, but I'll skip those for now. Just keep in mind these nonlinear oscillators work really, really well. You can implement it all. A lot of people have done it. Here's something that we have done. And, it just works, and it has this nice global stability property, meaning you can set it actually at 0 voltage and it would nicely go up to the desired solution. You can connect one, you add one, subtract one of these oscillators, and it would all nicely synchronize. Works really well. Let me now maybe get towards the end, the comparison, discussion, and conclusion. So I presented you these 4 types of synchronizing controllers. One is this droop control, so mimicking this proportional power and frequency behavior, which performs very well near steady state. But since active reactive power, frequency, and voltage are not decoupled, this performs really poorly. So it has a small region of attraction, if you want to use dynamics language. There's sort of the nonlinear version of that, which is virtual oscillator control. So you control the converters like coupled nonlinear oscillators, which works extremely well and locally reproduces loop control when you linearize it. You can emulate a synchronous machine, so you make a converter look in closed loop as if it was a generator, which is claimed to be backward compatible, but really only near the steady state, and it's not very resilient. Or the more robust version of that, you use that matching control, which relies on the duality of the DC voltage and the frequency. So those are the 4 classes of controllers that people have investigated over the last few years to how to robustly synchronize power converters. It seems to be a favorite exercise of graduate students and professors around the world to now run a whole bunch of comparison studies and simulations, maybe prove some theorems, maybe do some experiment and compare all of these. Then let me summarize if you look at all these papers, so my synopsis is that, first of all, you can make all of them work. All of them have essentially similar behavior in the small signal regime, so near linearization if you tune them well. It turns out that emulating a synchronous machine doesn't work really well. It has very poor transients, essentially because a converter is not a flywheel. You can try to emulate it, but it doesn't work so well. Turns out these VOC, so virtual oscillator control, has the best truly nonlinear large signal behavior in terms of very fast conversions, very robust. These types of matching controls relying on a duality of frequency and DC voltage are the most robust solutions, meaning it's really hard to destabilize them. And then maybe the conclusion is that what you should really do is some sort of multivariable control. We maybe combine the benefits of these virtual oscillators and maybe this matching type controllers that are based on these duality ideas. Okay, and now people actually came to that conclusion. Now there's various studies that actually do this multivariable control, say, let's combine the ideas of the physical duality and the virtual oscillators to construct very robust controllers. I have a few more slides on that, but I'll probably not go into this. I guess I gave you my main selling points. So a whole bunch of type of controllers which have been built and validated and so on. Maybe just coming to the conclusion. So this is really exciting research landscape between power electronics, power systems, and control systems, with lots of exciting problems here in the intersection. The problem I talked about today was building these synchronizing controllers, so-called grid-forming controllers for power converters. The take-home message is sort of a converter is not a flywheel, so don't try to emulate it. You should go for multivariable design. Don't decouple things. Don't close a whole bunch of individual loops, but think about multivariable control. For instance, the matching and the virtual oscillator. You should make sure you take constraints into account, so you don't want to overload the converter. And of course, you shouldn't forget about the DC voltage. And maybe as a last outlook, synchronization is only beginning, right? Yeah, you synchronize everything, good for you. But the next question is, okay, what do you do once you synchronize, right? You should also do something meaningful once you synchronize for a system. And I guess those are the next steps that people look into. This sort of concludes my talk. I hope I could tell you a little bit about power electronics and control design. And I hope it resonates with what you know about coupled oscillators and synchronization among these. Thank you very much.
Thank you, Florian.
Thank you, Florian.
You're welcome.
So are there any
Okay,
questions
Piero,
in the audience specific for this talk of Florian? Or if you have more general question addressed to all the two speakers?
So maybe I can start with a consideration and maybe a question for both the two speakers, just to break the ice. So I hope that other questions will follow. So first of all, I was impressed that both of you used the idea of analogy between different systems. In the case of Florian, mechanical and let's say power electronic system, and in the case of Eckehard, from neural network to power systems. So this is very exciting, and I think it's an important concept that I usually try to stress to my students. The powerful of the analogy. It's a concept which allows to really have a deep understanding on what you are studying, because you try to get the similarities and obviously also the differences, as it was really in a very good way pointed out by the topic of Florian. My question or stimulus for a small debate is the following. So we have seen in the nice picture by Florian this idea of bridging the research between different areas. And I think also Eckehard showed a lot of interesting phenomena which are really useful to understand what can occur in a power grid. These are nonlinear phenomena, but their analysis it's really important because they can occur, they can happen in the grid, and if you if you want to control something, you have first to understand what is its dynamics. So how can we reinforce this bridging and make more close the people working in this area, such that we have a little bit more cross-fertilization, and how this can realistically lead to technique which are then applied to real systems rather to be just published in wonderful papers.
Oh, maybe should I start?
Sure, go first.
Yeah.
Okay. Well, first of all, I would say our field of complex systems is very special in the sense that we are developing methods, fundamental methods, basic methods, rather than looking at specific systems, specific materials, like, semiconductors or whatever. And therefore, we can easily apply these methods to different systems. And this is one of the advantages, because in my case, neural systems and power grids are completely separate communities. And some work has been done and some phenomena have been found in neuroscience, and some work has been done in power grids. And we can profit from this by building bridges between the two. And once we've done that, we can also think of control methods applied, for example, to power systems. When we know what instabilities can occur. And in my case, adaptive networks show a plethora of novel, complex synchronization states, which were unknown hitherto. And so now we know what can happen. And once we know what can happen, we can think of control methods. And of course, the control community comes in. And we have seen in the second talk that there are very advanced methods of control, and we can then apply them. So maybe in a nutshell, in the field of complex systems, the perspective of complex systems is to use simple paradigmatic models together with complex network topology. And this is in some sense complementary to the traditional electrical engineering modeling, where one uses very sophisticated and detailed models, but maybe not the aspects of network science.
Yeah, let me elaborate on that and maybe provide the other perspective. So I guess I started working on these topics in 2009. The first papers I've written about were sort of, take these cool tools, say from Kuromoto type oscillators and apply them to stabilize or to study power system synchronization. And it was literally, there was a method out there that one-to-one matched the problem. And you could nicely combine them, right? Which was not obvious before. And you can write papers and so on, that's fine. But then when you go to the power system community and tell them about this, they couldn't care less unless you go the extra mile, extra 10 miles to make these methods then really useful for what they care about. So I had initially a lot of papers rejected, as you can imagine, meaning, okay, so you need to make the tools actionable. That is, you need to specify them to their more detailed problems, the detailed models, and so on. So the analogies and the methods definitely transfer. I fully agree with that. But if you want to have an impact in the actual application area, then I don't think it's enough. I don't think neuroscientists will care about if I bring a power system method to them, right? So you need to go the extra mile and convince the experts and, go then into the detailed specifics of the system.
I like to compare this to a hierarchy of modeling approaches. There is not one single model approach like Kuromoto or anything, but there is a hierarchy, and it depends upon the question you ask, how detailed you have to be. And in some cases, you do have to go to much more detail. And therefore, if you start with some simple paradigmatic models, you build on that and you elaborate that, take voltage dynamics and anything else. And then talking to the real world power grid people, you have to be as detailed as that in many cases. So I agree with you, Florian, that we can take something from the complex systems community, and then we have to elaborate on that, and we have to work hard to convince the real world power grid people that it's useful. And I have had similar experiences. Actually, it's not only the experience in power grid modeling, but it's the experience I've had in previous work, which I did on semiconductor transport and also in neuroscience. If you go to the community of neuroscientists or the community of semiconductor people, they are not satisfied with simple models and concepts as we are used to in complex systems, but they want to have detailed models. And then what we did a long time ago, 20 years ago, in the field of semiconductor transport, we also built that hierarchy of models where we have simple paradigmatic models, but the transport coefficients, for example, have to be calculated from more microscopic series. And I think this is the way we have to go. I believe it's useful because if you start with a very complex model right away, you don't see anything, and you won't be able to gain insight into, for example, the influence of the network structure. So we have to go that way, but it's not sufficient. I agree to stay with the Kuromoto model and then try to convince the rest of the people.
I think that this point is even more general than the specific problem we are discussing, because understanding that you can write down different models, so models are different hierarchical models, it's really important, because at the end the model is for answering a specific question, and in principle the more details you put there, the more accurate it is, but at some point you can miss the answer of your question because you come up with a model which is too complicated to deal with in an analytic way or things like that. So yeah, I totally agree with this point of view. Thank you.
Do you feel that the community of power systems and power electronics is getting more open to contribute, given the extra effort that, let's say, that it has been done to go towards the application? Are they getting more open to that kind of contribution?
I have personally the impression that maybe it's also because I'm adapting. I'm not sure if they get more open, I become more adapted. It's either or. But let me just give you a few examples. So I guess before 2007, 2008, nobody in power system used the language of graph theory. Right now it's quite standard. So they definitely absorbed some of the tools from the outside world, and they realized that, they were essentially lost in the forest and they couldn't see the big picture. And by going to more coarse grain models that other people bring in, they get new tools and new methods, and they saw the advantage. That is certainly true. Also, for this new power electron-dominated power systems, it's sort of a level playground. Nobody has the answers to these problems. It's not like someone in the industry who knows how to solve them. So they're very open-minded to come up with something in that particular problem domain.
I see. That's good.
I think we have to learn the language of each other. This is a major point. Initially we are talking different languages, and in order to understand what the other community is doing, we have to learn the language. And as soon as we both speak the same language, we can convince people that it's useful. And also we understand the real problems, the real world problems.
Yeah, definitely agree. Yeah. Do we have other questions?
So today our audience is a little bit shiny. It's strange.
I think it's a great it's a great time to talk about these things, because the Nobel Prize in Physics has given additional importance to our field. And
Eckehard, I should mention that actually Giorgio is a member of the Italian Society of Chaos and Complexity. So we are particularly proud of this. It's an honorary member. While thanks to as a way to thank you, we will offer to you as a speaker for this event the membership, the classical membership.
Thank you very much, Mattia. This is a great honor and a great pleasure.
It's a pleasure for us, especially for us.
Thank you very much.
And
I hope the emails are not in Italian.
And congratulations on the Nobel Prize to Giorgio Parisi and to you as the Società Italiana di Caos e Sistemi Complessità.
Bravissimo. Okay, Piero, I don't know. If we don't have other questions, I would just ask Fabio to share the screen with the slide for the next talk, just to announce it. Fabio is with us. Okay. So this is the one here. The next one, it will be 28 October, and it will be this time at 6 p.m. because our speakers are from US and from Israel and from US. They are Nama Brenner and Elisa Franco. They will speak about application of complex systems in the bacterial growth homeostasis and molecular feedback system. So different topics. Okay, so I think it's time to close, but not before thanking again our speakers. They were particularly kind to accept the invitation, and they also, I think, have done very beautiful talks from which we have learned a lot. So thank you, Eckehard, thank you, Florian, and thank you to all the participants for attending this section. Bye.
And thank you, Mattia and Pietro and Fabio, for bringing us together and for organizing this event. It was great. I enjoyed it.
Thank you.
Thanks a lot. Thanks a lot to you.
Thank you very much for hosting us.
Okay. Bye,
Thank you,
everyone.
Florian. Bye. Bye-bye.
Ciao.
Bye-bye.
Bye, everybody.